Shalom, my children. Today we are going to look at some of the other aspects of the ideal gas law. What is its implications? What are its other uses besides just solving an ideal gas scenario? Let's go ahead and get started with Dalton's law. Now, Dalton's law, named after John Dalton, the Dalton's law of the atomic theory, also did some work with gases. He was able to observe that the total pressure of a mixture of gases equals the sum of each individual gas. Taking that original Amedeo Avogadro example, where you could react a balloon filled with 2 liters of one gas and a balloon filled with 1 liter of another gas of oxygen to produce water, if you pop those balloons, you would generate pressures equal to 3 pressures worth of gas. 3 pressures worth of gas. And that has to do with the fact that when we add each gas together, we're just summing them up or adding them to each other. The idea being they're all taking up the same volume. The volume doesn't change just because we're adding more gas here. And the temperature isn't necessarily changing because we added more gas here. So the only thing that can directly change is our relationship of the moles and the pressure in this case. But from this understanding, we get the concept of a partial pressure. That pressure is usually used to think of a mixture of gases, the total pressure of all the gases in the room. Well, partial pressure is the pressure of an individual gas within a mixture. And a mathematical formula representing this law is just that the total pressure is equal to the sum of partial pressure 1, partial pressure 2, all the way to the nth partial pressure. However many gases are in the mixture, we sum them up to get the total pressure. Now, as I said, since the temperature and volume are not changing and R is a constant, we can directly relate the total pressure, to the moles. They're related to the moles. Now, because there is a relationship of an individual gas to the total pressure of the gas, we can figure out what fraction does the partial pressure take up. We can look at it as pressure of individual over pressure total. However, since pressure is directly proportional to the moles, we're technically finding what's called the mole fraction. Mole fraction. It's the fraction of moles that one gas is responsible for in mixture. It is essentially a percent without the multiplying by 100. What percent of the gas is from gas A? Except without the multiplied by 100. Well, what can this be good for? Well, the mole fraction can be used to relate the total pressure to the individual pressure and vice versa. You do not have to solve the ideal gas formula multiple times if you know mole fractions and a total pressure. A complex mixture with 5 gases, if you know the mole fraction of each gas, you can find out the pressures of each gas. So the following simple example. If I mix 1 mole of hydrogen with 3 moles of helium, the total moles of gas is 4. Well, in this case, 1 out of 4 is 0.25. 3 out of 4 is 0.75. Note that if I add the 2 mole fractions together, it should equal to 1. If I have this mixture and it's held at pressure of 1 atmosphere, that means 0.25 of those 1 atmospheres is hydrogen and the rest is helium. If I were to allow that to expand and heat them both up until the pressure is 4 bars, well then 1 of those 4 bars is hydrogen, 3 bars of that would be helium, because the mixture would change properties just the same regardless of what gas we have. So these following examples are utilizing this concept. If I have 3 moles of N2 and 1.5 moles of O2, and I mix together to produce 6 bars. If I add another 1 mole of O2 without changing the volume or temperature, what is the new pressure? So, this is a clever use of Dalton and ideal gas. There is more than one way to solve this. More than one way. I'm going to show you the simplest way, the most straightforward way. There is some fun little mathematical things you can do, but let's look at this. 3 plus 1.5 total moles of gas is 4.5 moles of gas is proportional to 6 bar, because P equals N RT over V. Now, if I were to add another mole, it would jump up to 5.5 moles of gas. And so we want to know what is the pressure. Set up this relationship that 6 bars over 4.5 moles equal to pressure over 5.5 moles. So if I'm moving that up, bless me, I will get the pressure. So 6 times 5.5 divided by 4.5 means my pressure must have increased to 7.33 bars. That's my increase in pressure. Now, this is another example. This one utilizes vapor pressure. Vapor pressure is a unique property. It is the pressure of water vapor in the air that, unlike the other pressures of gases, water vapor only depends on, 1, the availability of there being water, and the ambient temperature of the water. That the vapor pressure of water depends on the fact of what temperature is the water in the room. That water will naturally, some amount of water will naturally boil at room temperature to generate some vapor pressure. So in this case, this is independent of all the other gases. Now, the equation reads, if 1.5 liters of oxygen is collected under 35 degrees of water, 35 degrees, at a total pressure of 755 torr, 1, what is the pressure of oxygen, and how many moles of oxygen is that? So we need to look on that chart. What is our pressure of water? We have to look at our temperature. At 35 degrees, the pressure of water is generated as 42.175 torr. So looking at that, we have all we need. Okay, so now, so the pressure of oxygen plus the pressure of water will have to equal 755. So that is the temperature on the outside. So PO2 plus 42.175 equals 755. Subtract these two and I get 175, and I get 712.825 torr. Now I'm going to go ahead and quickly convert this into atmospheres. Not 1 atmosphere, but a little bit less. This is equal to 0.938 atm. Okay. That's the first question. The second question is, how many moles of oxygen did I actually collect? So PV over RT equals N. So 0.938 atmospheres times 1.5 liter R8206 atmosphere liter mole Kelvin, and our temperature 35 plus 273 means we have 308 Kelvin. So I know I say so a lot. When I multiply this by 1.5 divided by my R divided by my temperature, I collected a very small quantity of gas. But it is more or less pure oxygen. Very little amounts of water, 0.0556 moles of pure oxygen. Okay. What else are we able to do with the ideal gas equation? If you know the density of the gas, you can calculate its molar mass, or using a molar mass, we know the approximate density of gases. Now, density, remember, is an equation that says mass over volume equals to density. Well, mass is simply moles times a gas's molar mass. So exchanging the mass for N times molar mass, you get density is equal to moles over volume times its molar mass. Well, rearranging this equation to more closely represent the ideal gas law, P over RT is equal to N over V. So exchanging N over V for P over RT, we get that density is the gas pressure times its molar mass over R times T. So that the density goes up when the pressure goes up, but the density goes down when the temperature goes up. As it gets hotter, it becomes less dense. That's basically why hot air rises, because the temperature is going up, the density is going down, it floats higher. So, at standard temperature and pressure, what is the density of 1 mole of xenon gas? 1 mole of xenon, and we want STP. So, to look this up, we need a few things. density equals P times mm over R times T. Standard temperature and pressure is equal to 1 atmosphere and 273 Kelvin, or 0 degrees Celsius. So we have everything we need except for our molar mass. 8206 atmosphere, liter, mole, Kelvin, 273 Kelvin. So the last step is just a quick look this up. Well, let's look it up. Easy enough to do. We look up xenon. Xenon weighs approximately 131.3. 131.3. 131.3 grams per mole. Well, the per mole cancels out, the Kelvin cancels out, the atmosphere cancels out, and we're left with a mass and a volume. So 1 times 131.3 divided by R divided by T gives us a pressure of 5.86 grams per liter. That seems a tad high. Well, in terms of our gases, it is a little high for a gas, but you think water is 1 gram per milliliter. But the key here is that units are grams per liter. So, gram per milliliter, that's like saying there's 1,000 grams of water in 1 liter of water. So the density of xenon is much, much, much less than water. It will float over water without a problem. But in terms of other gases, it will sink. Last slide, let's just look at one other aspect, is that we can combine gases and think of them in terms of a chemical reaction. We can use our ideal gases to figure this out. Now, just like it is possible to convert atoms to moles to grams, it is possible to convert grams to moles to pressure, or grams to moles to volume, assuming all the reaction conditions are known. And much like Dalton's law of partial pressure, there is a Gay-Lussac's law of combining volumes that relates gas volumes to their moles, assuming the external pressure and temperature are constant. So it's possible if I had 110 grams of ammonium carbonate, if this decomposes under conditions of 35 Celsius and 1 atmosphere, what would the volume of each gas be? Given that the reaction produces ammonia, 2 moles of ammonia, 1 mole of CO2, and 1 mole of water. Well, you turn 110 grams into moles, and then you can find what would the volume be of CO2. Because once you have mole times temperature divided by mole times temperature times R divided by your pressure is equal to V. You're basically saying V equals nRT over P. And you can find that out. And because they're proportionally via moles, the amount of water is going to be equal to the amount of CO2. And the amount of ammonia is twice that of CO2. So you can produce a lot of moles of various gases under these conditions. But that is where we will stop for this particular video. The last video will deal with the theory for the large part.